Hello and welcome back to Compiler Programming. Today we are going to work on some Windows memory allocation stuff. And to explain you why that is even important, let's run some benchmarks. So first let me compile in release mode because that's where the performance is actually interesting. And then I have like the two tests. One tries to constant fold 1 million once, and another one tries to compile a function that contains 1 million calls to another function, basically. So we have this folding, and it takes around, well, let's say 760, 770. It's a bit faster when I don't stream, but it's fine. But we are interested in our relative numbers anyway. And then we have another one, which is, as I said, 1 million calls to another function, which is just an empty print function, but doesn't really matter. And this is around 1.4 seconds. Okay, so I was looking at the profiles, and I don't have it open right now, but the thing is, we spent almost like 20 to 30% of time inside of operating system, and considering that both of these programs don't really have any compile time execution to speak of, that means that and reading a file takes I don't know, 10, 20 milliseconds, something like that. It seems that all of the time that is spent in the kernel is actually has to do with memory, which is really unfortunate. And I mean, obviously I can reduce memory usage, and it's something to work on, but regardless of that, it is important that if the compiler does consume a lot of memory, that does not slow down much. And right now it does. Okay, so let's take a look at here. This is my sort of allocation buffer, and you'll see there is some code below it, but let's not look at it. Let's just say, so this is what the main arena I use for allocating all the objects. And majority of the time, when we do allocation from this thing, we are actually it's just a pointer bump essentially. If we look in here with this virtual buffer memory make, right? And if we look at allocate, where is allocate bytes? Yeah, so it does some alignment check because it has to, sort of. And then like we could technically have more specialized buffers, but anyway, the main thing here is that if it is committed, so if this check actually is false, then none of this happens. And as you can see, there are no other conditionals, and it's just like it is bumps the pointer, more or less. So this is great, but turns out that the issue that you run into is in the way that at least Windows manages memory, and Linux to the same degree, but the fix that we're going to do today is probably going to be only for Windows because it is slightly easier, I think, and I'm less familiar with Linux type, but I think it can work there as well. But first let me explain what happens here. So when you request some memory from the system, when you're doing, where is this thing? So when you're doing this virtual alloc call, right? So what actually happens is that you get, let me add some kind of comment. So you get a chunk of memory, right? And let's say that this chunk consists of some pages. So memory allocated in pages, usually they are 4 kilobytes in size, at least in Windows right now, unless you use huge memory pages, but we can ignore those for now. And so when you ask for this stuff, there are two things you can do. You can say memory reserve, And my reserve will just, so let's say this is like address 0 or A, and this is A plus reservation size. So when you say reserve, it just adds sort of an entry into a special kernel table that says that address from A to A plus whatever are now reserved for this particular process. Nothing happens. There is absolutely no guarantee that when you actually want to commit those pages, that nothing happens. If you add mem commit, from what I understand, and it's not very well documented, what happens is that the system will guarantee that it will give you a page of memory when you try to access it, but when you try to access it, but it doesn't guarantee if it's going to be actual random access memory, RAM, or it's going to be something from the page file from the swap. But the actual allocation of physical memory page, or like loading something from swap, happens when you access this. So when you actually read or write to a particular page. So a page fault happens in the kernel, and like you could theoretically install your own page fault handler, but it doesn't really matter. The point is that whenever you actually try to read or write to a committed memory, so not just reserve, but also commit here, only then the system actually allocates the physical page. And that is, well, first of all, the actual process of allocating the physical page is not fast. But another problem that exists there is that you sort of, whenever you try to access it and a page is not yet there, you have the page fault, which is like an interrupt handler. So you are hard thrown into the kernel, and the kernel has to like save all of your state, then do actual page setup, and then bring you back into execution. So that's not cool. And the next question is like, how bad is it? Like, is it really that 20 to 30%? So one idea that I had was that, okay, it's fine. I'm gonna I can't really do anything about these page faults from my understanding. There isn't really a way to easily force like a real page allocation for this memory. Maybe there is like more advanced APIs that I don't know about to deal with, like memory mapping. Maybe you can like deal with physical pages there directly, and it's something that I can look into. Maybe that would be a better way to deal with it. But even then, you would still incur the cost of actually associating a physical page with the virtual one. And moreover, you like the kernel, also something I forgot to say, that whenever a page fault happens, it associates the physical page, and it also mem sets this page to 0. And because if it didn't, like you could just randomly read the data from some previous application that previously had this memory page, which is not something that is cool with any kind of security, right? And like all of these cost cycles, and it would be cool if first to minimize it, and secondly, if it is not minimizable, to try to offload this to a different thread or different CPU core. I think you will, if you do that, you incur some cache problems, probably because you will be like, it is really hard to say like if that's actually going to be a problem or not, but let's just say it might. the ultimate question is, will it still be faster? So that was a bit of an introduction, and if you're not so familiar with the topic, that might be a bit hand-wavy, but let's just get to the point. So we had our kind of benchmarks before, right? And so I wrote a bit of code, and this is not the code that I actually want to have in the compiler. I wanted to have something smarter, but this should give us sort of the maximal performance gain that we can expect out of something like this. And also show some problems with just doing it the way I'm doing it here. So what's happening? Well, when we allocate the buffer, and as you can see, we are allocating 16 gigabytes of space, and this just does memory reserve. So we are not even guaranteed that we will have a swap or a physical page available when we try to do commit. Then in this new block, what we are doing is we are committing 1 gigabyte of memory. Like we are actually saying, Windows, I need a guarantee from you that whenever I access this 1 gigabyte range, you will give me something. You will either give me a real physical page. I mean, it's always going to be a physical page, but you can swap it out to disk if you need to. But this range of addresses is now valid. So this does this thing over here, where it's just okay. I will guarantee that there is going to be a valid address range, but by itself it doesn't do anything. And we can see that it doesn't do anything because if we try to compile this in release mode, and it takes a while, so bear with me. But right now is that we are just asking the system to promise that it will give us a page when we ask to, but it doesn't actually do any assignment or any zero of memory. Now we can try to run the print. I think that's the most interesting example. And I mean, there is some varieties, so maybe it helped a bit. I don't know, 20 milliseconds, like it's hard to say. It might be just variance, but didn't do almost anything. And that because the actual cost of page faults and memory zeroing is not paid here. So what can we do instead? Well, we have lots of cores on our CPU. I think I actually have 6 core, but 12 thread. So it has the hyperthreading, and I think that's actually fine in this case. But empirically, I figured out that 8 is the best number for this. But what does this thing do? Well, this is a very stupid way to spawn 8 threads and wait for all of them. Like, this is not how you do it, so don't look at this code. It's terrible for that. But I wanted to have something quick and dirty and not going into Windows-specific APIs to just try it out. But anyway, this spawns 8 threads and gives each of them an 1/8 of the address range that I wanted to allocate. And then this thing, all it does is it walks through that range of addresses and tries to read from each page, from the first byte of each page. Okay, as I said, as says in comment, we need to have Volatile here, because if you don't have it and you run optimized build, the compiler will just remove this memory access, because it says, well, there is no actual reason to read from the memory. I'm still not 100% sure that Volatile guarantees that the read will happen. I think so, but it seems to do that in Godbolt when I check, and it works empirically. Anyway, so yeah, this just literally does sort of nothing except trying to read from the memory. The reason I'm saying that this is a bit more complicated on Linux, because if I try to do this on Linux, that would not do anything either, because Linux actually maps all the pages to a 0 page, so I will just get 0 when I try to read it. And in a sense, that might be a better behavior, but it also will complicate my life here because I can't read. I need to write. And if I need to write, that means I will need to have more synchronizations once we get to actually using this stuff later on. But that is for a bit later. Now, okay. So we have these 8 threads. Let's build again in release mode. Yeah, takes a bit of time. Clang, I think, adds around 30 to 50% performance, which is quite a lot for this code compared to Microsoft's compiler, but it is very slow in release mode. And I only have a single compilation unit. Okay, so getting back to this thing, now if we try to run the same thing, and we are not getting any performance benefit out of that. Now that is quite interesting. That's because I didn't actually save the file. Sorry about that. We'll have to suffer through Clang compilation one more time before we jump into actually implementing something better. Okay, now, so as you can see, that is 300 milliseconds off. It's like 25-ish%. When I tested without streaming, which I think consumes quite a lot of CPU stuff as well, it's even bigger, the difference. So you might say, well, just keep it like that. Well, it's not great because that means that I'm incurring the cost of this stuff and I'm always consuming a gigabyte of memory, even if I don't need it. And you can see that it is actually hurting you when you try to do folding, which is now 827 instead of 772, right? So it sort of lost 50 milliseconds of performance, which is like, I don't know, 7-8%. And it is going to be even worse for smaller programs. So that's not great. And obviously, yeah, it just doesn't scale. I can try to do some kind of estimation. It's like, oh, if I'm trying to compile a program that's roughly this size and whatever, but it seems like not a great way to do this. So what I thought was, well, what if I, my compiler is single threaded right now, so I have another 11 threads on my machine, and newer machines have even more, just sitting around not doing anything. Would be cool if I could ask them to run ahead of what I actually need and commit those chunks of memory. Now that might be a bit abstract, but we will try to make it work. And I think we will go ahead and work on this directly in the allocator because it will need to have sort of more things. Need to know internals. Okay, what is this going to be? So I'm tracking the reserved size of the memory. I'm tracking how much is actually occupied. Then I'm tracking the committed size, so what was called with memory commit. And then this is sort of how much ahead I commit each time I sort of run out of the committed space. Okay. So what are we going to do? Well, we are first of all going to put a thread and say this is warmup thread. Okay. What is this thread going to do? Well, it will, whenever we init the buffer, we will also try to create a thread. And this is sort of an interesting thing that I think would be nice to use Windows specific APIs. So should I use the generic thread here? I don't know, doesn't matter. Let's just make that happen. Okay. This is kind of awkward with if devs, but that's fine. We can say buffer thread is thread make. That is, do you use thread make? I guess I do. Okay. Thread make, and we need to pass it some kind of callback that will run in this thread. So let's just try this. I will start with the most sort of stupid version of this, and then we will hopefully, if we get any benefit of it, that would be great. Then we can get progressively more complicated, or I might leave it as an exercise for myself for later, because any kind of threaded code is kind of finicky, and here, like, you would want to make sure that whatever happens with the threads here, it does not interfere with the super fast allocation that arenas actually give you. So that is something to consider. Anyhow, static void, virtual memory buffer, warm up proc, and it accepts void star data. And here we need to create some data, which is going to be void star. Well, let's just have it like this. Virtual memory buffer is data, and now interesting thing. So what I want to do is sort of look one commit step ahead. So this is going to be a bit awkward to do, but let me again make that picture, and I think it would be nice to keep it as documentation anyway. So here we have something like virtual buffer is committed in steps of commit step byte size. The diagram below each cell in the diagram below represents one such step. Or is it the good way to deal with this? No, let's just try this out. Each cell can be in one of three states. First, reserved. 2, committed. 3 warmed up. Physical or page allocated. Allocated and zeroed. Next, what should happen basically is that when the buffer is created, we want to okay, when ensure committed is called, we transition from 1 to 2 and also signal to the warmup thread that we want to warm up the next step of the buffer, something along those lines. Okay. So that the diagram always looks something like that. And we have in this, we have W, and we have C, and we have R, 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 R. Something along those lines. I hope this makes sense. If you will still have questions after watching the video, leave them in the comments. I will happily answer them. But for now, let's continue. So this is a basic comment of how this works. I also need to describe how synchronization works here. But for now, what we are going to do is we are just gonna take this code over here and going to say that, so we have a buffer, right? And so we can say S8 star start address is buffer memory plus buffer committed minus buffer commit step byte size. The one thing here is that if you change any of these values, you're gonna really screw up this process. So ideally, they probably should all be const. But that's something for me to think about. So to do, maybe make buffer fields const or something. Now this is a start address. So we would do it like this, and then we say 0, location is start address plus offset. Okay, so that seems fine, but the problem that we'll have right now, I think, if we try to run this code, is that it will just consume crazy amount of CPU, because this thing more or less well, let's make it already fine. We'll just say while true. We do this, and these probably need to be atomic, to be perfectly honest with you. I think it's okay on x64, but yeah. And then to do make committed atomic, I think. Okay. And here we would just say sleep 1. I don't know. Sleep 0. Sleep 1. I don't know what would be a good thing here. Ideally, probably I would want to have some kind of more direct synchronization, but I don't want to go into that. So right now, let's see if this even helps us at all. And I might also have to play around with the commit step byte size so that this thing sort of runs ahead in like it has a larger window to run ahead so that the other code doesn't catch up with it. But let's see if that is important. We do this and we give it the buffer. Okay, does that even compile? Oh, of course not. So I guess the thread code is below this. No. Maybe. Thread. Yeah, threads are very much below this, and that's something that I need to actually move very high up. At least it can be moved very high up. So we have numbers. That's fine. We have atomic. We can move it here, I guess. No, it needs to be after allocators. Integer casts as okay. Here are the allocators. Be a good place for it, I guess. Okay, thread is not a member. Yes, that's because it's called warmup thread. Okay, well, I guess that is it. I'm not sure. I think that all threads will quit automatically when the process quits. So I don't think I have to clean this up, but let's see. And also let's see if this even works. Or if it does anything. Well, I guess there's only one way to find out. First of all, I think I will run... Oh. Yeah. So... we probably want to destroy this thread. That's kinda awkward. So in 32 destroy thread, terminate thread. Okay, terminate thread, exit code. And I must have thread terminate access rights. I hope it does. So let's do it like this. Let's actually use Windows APIs, I guess, directly. So we'll just say void star, and then I'm gonna look for thread, and here we can take a look at this proc and data. Wrapper proc. Because we want exit thread of 0 here. Right. Okay, we actually don't want that anyway, so I think that is fine. I can call this directly. Okay, so what do we want to get here? We have virtual memory proc, and I guess we have buffer. And then when we do here, we just say terminate thread of buffer warm up thread. I actually create quite a few virtual memory buffers, so that might not be what I want anyway. Like I want it to be conditional, and I just say like this buffer you actually do want to do this warm up stuff. Maybe it should be not part of the buffer and somehow from the side, but it's something I can figure out later. Right now I'm interested if this will work at all or not. So that's this build. Red, no, it's not void, it's void star. Legal use of type void, that's because it needs to be a void star. Now p thread start routine. Is the thing. Oops. Per thread proc. Oh, it needs to return a D word. Okay, I guess the D word is the return thing. Fine, I can do D word. That's okay. Okay, that builds. Well, let's see what's going to happen. Actually, I probably want to run tests. Yikes. Something did not go well at all, I have to say. Okay, let's see here what actually happens. Yeah, here we need to also say if buffer committed less than commit step side, then continue. Because I think what happens is we started here, but at this particular point we don't have anything committed, so nothing actually happens. Something like this, I think. Okay. So that is fine. I think now there is another race here where I do terminate thread. But now I need to also do wait for single object. If I understand correctly what is happening. try that. Okay. So this is not going great so far. Let's take a look at what the state of the buffer is right now. Buffer capacity, that is 16 gigabytes, I think. Yep, it is. We have occupied, committed, commit step size. So here everything is sort of fine-ish. So it looks like somebody offset start address plus buffer committed. So what is start address here? Oh, okay. Right, first of all, this is wrong, what I'm trying to do. And secondly, so I guess we need to know what the warmup size is. Say warmed up. And here we would say if buffer warmed up is less than buffer committed. No. Is more equals. Technically it's just going to be equals, but that's fine. Buffer warmed up is more than buffer committed, then we, what do we do? Well, we say that plus buffer warmed up. So let's just say U64 delta is buffer committed minus warmed up, and here we use warmed up, and then we don't do minus, and then we say delta. I think there's still a bigger problem, like there's more races here, but that's fine. Offset delta offset. I think that is correct. And then we say buffer warmed up is buffer committed. Oh yeah, right. I think I know what the issue is. Maybe. Let's just enable this for one buffer, and the way we are going to do that is saying this. So we would make this conditional, and then we would say, we'll take this code, and we would say static inline void virtual memory buffer enable warmup. Like so. Is this gonna work? I wonder. Well, right now nothing should, like, it should work just fine because we're not actually doing anything. Right, okay. Right, but we are still not doing anything because now we need to go over here and actually do this. Enable warmup of these jars. I'm actually not very proficient with threads. I understand the theory, but I still have lots to learn about all the synchronization stuff and what I can do, what I can't do, what is okay on x86-64, what's okay generally, and so on and so forth. So I'm just very much a novice, and this is one of the reasons why the compiler is generally single-threaded, because I just not very good at this kind of stuff. I spent most of my career writing JavaScripty things, and that is very much a single-threaded. Anyhow, let's try to run this again and see how badly that explodes now. So it still explodes, and what's worse, there is no stack trace. Like, it just tells me that this thing is... Well, right, of course there is no stack trace, because we don't, like, this, some other thread did something and that made this one very unhappy. Okay, what can I do about that? I mean, I can try to do a better synchronization. How would I go about that? Well, I could do something like atomic E64 and say I think it's time to go and dive into the documentation from the Windows. So there are a bunch of synchronization primitives. I've almost never used any of those, so it is all very much new to me, so expect me to be very frustrated and annoyed about all of this, but let's start. So the way I understand, the event is sort of what ideally I would want for this synchronization. It allows me to say to another thread that you actually should wake up now, and then it does something and it goes back into hiding. I'm pretty sure I'm doing this wrong, but I also don't know how to do it right, how to wait for a terminate thread, if that makes sense. Maybe... So if succeeds, value is non-zero. So let's do this. And then we probably will get the assertion if I misunderstand this. Oh, I'm stupid. Duh. So I freed and then I... That is stupid, but let's see if that is what is actually the problem. And it is. Great. Okay, so that was just a stupid thing on my part. And I think this is the stupid version of this stuff should actually work. Now the main question is, did it do anything for us performance-wise? That's something we can check. Just need to wait for Clang to finish it. Now I said, like, this is stupid. Like, this is not how you would want to do this because it wastes a bunch of CPU cycles and it's not great. There is like no proper synchronization, so just don't look at this code. The question is, does the idea work? And for idea, if it does work, probably that should be enough because this thread should just waste another core anyway, and that is fine for testing, but let's see if that is actually true or not. So we can start with the interesting one and run print. That does not look very good. So we have 1364 here. If I disable this, see, try to run print. Well, I mean, maybe, sort of, a bit. I guess we shade off like 50 milliseconds, but that's not particularly great. But I think now the problem might be in here, that sort of by the time the thread wakes up to realize that it needs to do stuff, we already occupied majority of this memory anyway. So what I'm going to do is I'm going to try to increase this size and see if that makes any difference whatsoever. I mean, ideally, like another problem is right now this is not overlapping. So as soon as we hit the committed one, we actually yeah, I will try to explain better with a comment now if this helps. Okay, so yeah, as I expected, increasing this window helps, but I think right now the big problem is that they are racing each other when we do commit. So if we look back here, where is this? So when this happens, we update the committed here, right? But the main program starts to allocate memory and starts to also cause page faults itself straight up. And depending on exactly how long this thing sleeps, it might be that it doesn't give as much to us as we would want. I can try to do sleep 0, but I don't know. Let's see what that is. Right now, from here, basically what I will need to figure out is what is the right way to signal to this warmup thread that it needs to do something. Should it just like run in the background like this? Should I explicitly send messages? The problem is explicitly sending messages will slow down the main allocation loop, so it's also not great. But it's something that needs to be very carefully measured and to see if that helps or not. So switching to sleep 0 doesn't do anything for us. I can also try, I think it's called something like, yeah, there is switch to thread, which is another way to yield. which is even more hardcore. So that will probably make one of my CPU cores spin like crazy. But this is something that we can try to check. Yeah, so that does not seem to do anything good for us, and the sleep one seems to have been the best thing. I think, yeah, let's add this to Git. And one final thing I can try to do is I can try to add this overlap. So again, what happens is when we commit something, yeah, we will start to try to read this memory from two threads, and that's bad in general. And we will write from the main thread and then read it in this warmup thread. So this is not cool. Ideally, the chunk of memory that is being warmed up is always one hand, sort of. Now that will require changes to how all of this stuff works. How would I do that? So when I do commit, what do I need to do? I need to commit twice as much as I would want. So I guess I will need another variable or another field here. How do I do this in the best possible way? So one thing I can do is I can just loop on warmed up in the allocation, but it's not great. It's better if it's always sort of one step ahead, and that will need to committed and warmed up. I guess. Let's try this. For this to work, when we commit, okay, buffer committed. Size is more than buffer committed. Yeah, okay, that's fine. Here we would say okay, so what we'll actually do is when we start the warmup, we will ensure that it's committed. So let me move this here. Yeah, so we say buffer, and then we will give it buffer committed plus buffer commit step size. This probably needs to be more than equals, because if the size is exactly the committed, then it's fine. So let's try that. Okay, so we ensure that it's committed. One more step from what it was before, and then we start the warm-up. It's fine. Now when we do the commit, this is where we need to have a logic to do something different if we have warmup or we don't have warmup, I think. So if we have, let's just do the stupid logic here. So commit pointer, that's fine. Size more than buffer committed. Okay, I think I know. I think I know how these all should work out. So what we're gonna do is we're gonna remove this, and we're just gonna say committed and warmed up. Buffer committed and warmed up. Then we continue. Then delta. No. Well, then we don't need warmed up. So actually it is this thing. If committed or yeah, okay. Okay. So we do this. Okay, so here this is actually committed, it's fine. And here we would say committed, okay, that will also be okay. In here, we check if it is more than committed. I don't know why, but this is just completely breaks my brain. If we have more than committed, then we need to do another. Yeah, so if size is more than committed and warmed up, yes. Then we do this. Required to commit size. This is actually wrong. No, this is fine. Yeah, we align it. We don't reserve. Okay, so we align this. Okay. Okay, so we do the like this. So we make this one head. We take the size. We add to it another thing that will be used for warm-up, and then we align all of that jazz to the commit size. That's fine. Now we need to have another step where we say that required to commit is U64 min of buffer capacity and required to commit. So what here we also want to make sure that we don't run over, in a sense, like when we don't try to warm up the part outside of the end of the buffer. Maybe that deserves a comment. Make sure we don't overrun the buffer when doing the warm-up. Okay, so we did this. that is fine. And now this is our commit pointer. So here we will actually use committed. Yeah, that is correct here, I think. And then buffer committed and warmed up is okay. So which kind of cases we have? We try to allocate, and we have warmed up space for that. Great. We want to do it this way, or do I not want to do it this way? Maybe a better way would be no. Let's not do it this way. I don't like how that complicates the rest of the stuff. Would be great if we can keep the complexity in here. And the way we're gonna keep complexity in here is by doing what? Let's see. We don't need this thing, I think. Right. So if warmed up is more than buffer, so if it is equal to buffer capacity, then we can actually do exit thread of 0. Like there is nothing for us to do. Like we literally warmed up the whole buffer. So there is absolutely no reason for us to continue. So that's good. Next, if buffer warmed up is more or equal to buffer committed plus what? Plus buffer commit step byte size, then we continue. So this is, we are looking one ahead, and if we warmed up more than one ahead, then everything is fine. This still needs to go below here. Okay, so if we, yeah, if this is, yeah, so if this is warmed up, actually it should be like this. See, so if we are warming up here, what's it called? Like, how do we call it? In progress of being, let's call it marked for warming. That's how we're gonna call this. So it is gonna be, yeah, we have one that is warmed up, we have one that is marked. Actually, yeah, then we don't really need committed. We just have marked for warming. So this like this. Yeah, okay. That makes sense, I think. So now this is fine. I need to think if we still can have problems with capacity. I don't think so, but I'd rather be cautious because here it doesn't cost us anything. So if buffer committed is buffer capacity, and here I guess I can do this just in case, then we continue. Okay, now like this. So now we say that warmed up is this. Let's again be cautious here, and we say buffer capacity. So we clamp it. Then we do this. Buffer committed minus buffer warmed up. That makes sense. Then we do warmup. And then we update this. Actually, we don't need to update this now. But we do need another condition. If warmup is here, we do need to continue. So I think now it should make sense. If warmed up everything, exit, we don't care about this. If if we warmed up one ahead, we don't do anything and just continue sleeping and looping. If committed is less than capacity, then we say that we're gonna warm up one ahead, and we make sure that we don't overrun capacity. We shouldn't, but better be safe than sorry. Next, we figure out how much to warm up, and we warm it up. Yeah, I think that makes sense, but whether it does or not, that's something we'll figure out by running it in a debugger. And I guess I have some issues because I cannot spell committed apparently. I'm not even sure I'm spelling it correctly, but it doesn't matter. What matters is it builds and we can run it. And we crash. Right, because I didn't do the most important thing, which is doing this. Now, this is sort of a bit useless in a sense. Oh, this is very wrong. Oh no, this is fine. But this is warmed up minus committed. So it needs to be like this. Yeah, now it needs to be like this. We need to commit it. So we say delta and StartAddress. Okay, I think this is good. So yeah, we go one ahead, we commit it. If it wasn't, well, it shouldn't be, but this is, we can call it multiple times and nothing will actually happen. I think it's totally fine to do that. And then we do this stuff. Okay, let's try this again. Okay, cool. So that works, which is great. Now we have 1264, 1235 to beat. Let's compile it with a Clang and see what we have. Well, oh, yeah, great. So I think that's better. It is sort of moderately better, but it is better. We were at 1235 and now we are at 1180. We can try to run it a couple of more times. 1162. That's great. I'm pretty sure that it will get more stuff when we are done. But now, yeah. So unfortunately, I can actually test it. So what I want to do is I want to compare with this version, right? Because this was sort of the best case scenario in a sense. So let's try to compare it with this stuff. We still have it, and we can try to do something about that. Need these performance counters. Okay, that builds. Now we then need to build it in release mode and wait for that. But that should allow us to compare how close are we to this stuff. So is our parallel thread thing actually as best as it could be, or is it worse? Well, it looks like we got pretty much on the spot. I mean, there is some kind of variation, but in general, like 1171 there, 1144 here, I think this is slightly better. But it is so marginally better that it is great. Now we can try to run the folding one and compare how it behaves. So with the 8 threads trying to run, we have 853, so it is kind of not great. And if we try to do our warm-up thread that just runs ahead, we can try to do this and see how we are doing. Again, not very fast. And yeah, so this is great. This is perfect. I definitely didn't lose performance. I think I actually gained performance compared to, yeah, I don't have, unfortunately, the original one, like without any kind of stuff. But here we are definitely doing much better. It's almost there's more than 100 milliseconds between those. So I think it was like 7% worse, and now we are about 15% better. So this actually helped the smaller test, and in even smaller tests it will have much more effect. So this is great. I'm very happy about this one. There is definitely still stuff to do in the synchronization. Like this is terrible code. Again, don't look at it. I will spend a bunch of time now trying to make sure that there are no races and everything is as it should be. But as a first draft, as proof of concept, this definitely works. I will use it in my other projects. I think that all allocators should have something like this, because I mean, in a sense, yeah, I think that it just makes sense now. Previously, when the CPUs didn't have many threads, it was probably a bad idea to have a thread that just sort of does GC, in the sense like reverse GC. It allocates memory for you. But I think now it is a good idea to do something like this. But I will, see how it feels later on and go from there. So yeah, this is all I wanted to do today. I know it's a bit of a different thing from my usual stuff, but I thought it's an interesting idea, and it definitely helps the compiler, so I'm pretty happy. If you stuck with me through all of this thread weirdness, then thank you very much, and I will hopefully see you next time.